can we use all this theory to study electric field, of course. And remember that we can easily measure electric potential relative to ground. We have a device for that. So if we use that device, it doesn't work. If we use that device, it works. What can we do? We can measure electric potential in a certain region at different locations and find many locations with the same potential and draw the first equipotential line. Then we can move on and measure electric potential at other locations. We find locations with a new but the same potential. And then we can repeat this procedure again and again. And then what we do, we can apply the rules. For example, electric field line should be perpendicular here, and then here, and then here. So we can kind of show how electric field looks like in this region. And electric field lines. And now what can we do? Well, we could ask a question, for example, what's going to happen with a positive charge if it was placed here and released? It will begin moving in the direction of a force. And as we know, now, for the positive charge, electric force points in the direction of the field that is represented by electric field vector. That's electric field vector. This will be electric field force. And that means this charge will begin moving, well, in that direction. Well, let's do that. Let's map electric field. Fingers crossed it's gonna work. Recognize this device that measures electric potential relative to the ground. For example, nine volts. Well, it's a fresh battery, a little bit more. What I have here is a standard power supply for a computer. I need to use it to generate electric field between two electrodes. Well, first I need to create that electric field. I need an electrode. So it wouldn't be moving, actually. Clamp it. Alright. And I want to insulate this from my region with electric field. Now I need wires. So I need to connect. Where's my second wire? Which is better? I just remember. This will be connected to the outside. This will be connected to inside. The issue, the difficulty is that inside it actually has to be connected to the outside of surface of inside. So I have to spread it. This is the hardest part. Let's see. Now, let's see if I've got a good connection. Yes, I do. The potential difference between these 2 points is 20 volts. But, well, it's going to be easier for me if one will be connected all the time. So I could move another one. Connection is still here. But nothing, basically nothing, zero. Because this paper is not conductive. This is just a regular paper towel. But I need to create electric field. So this is what I'm gonna do. I've done it before, you can see. And when I've done it before, it worked. It doesn't mean it's gonna work now. It does work. 8, 5, 12. So what can I do now is points with the same potential. For example, let it round to 13. Where is 13? Another one. No, wrong direction. 12.9, 13. Good enough for us. Oops, this is the wrong one. Now, we can go to the next point, 10. Okay. What is the next 10? Not 10. 10, that's 11. 10, good enough. Of course, in reality, you would have to find more points with the same potential. And you could repeat it again and again. You can see that when we move away, potential changes. Now what can we do? Draw 2 lines. These 2 lines represent equipotential number 1, equipotential number 2. And now we can draw a electric field line. I forgot. That was the higher, that was lower. So this is high, this is low. So electric field should point from high to low and has to be perpendicular. And with a good equipment, you could repeat this procedure again and again and again and draw electric field lines in the whole region. Good job. Now what do I do? Okay, first switch back camera and start sharing screen again. And of course, we could do even more than just drawing, because if we measured electric potential at different locations, for example, it was 13 and 10, and if you find 2 locations close enough on the same line, and if you measure distance, which is about 3 centimeters, the distance between these points, 3 centimeters, we actually can make a pretty good estimation for the electric field strength, because it will be equal to difference in potential divided by distance. In our case, that is 13 minus 10 divided by 3 centimeters, 0.03, which makes it 3 over 0.03, which makes it 100, a volt over a meter, or 100 Newton over a Coulomb. And we could even calculate the strength or force acting on an electron placed there. If I place an electron, the magnitude of a force acting on this electron right there will be equal to the magnitude of a charge times electric field. So it's going to be 1.6 times 10 to the negative 19th times 100, which is 1.6 times 10 to the negative 17th newtons. And if electron is not bound to anything, it should start moving. In what direction? Up, opposite to the field, because as we know, an electron is negative, so the force acting on it should be opposite to electric field. And if we have many electrons, they would begin moving in the same direction. And that's what we call electric current. Our next topic